Okay, in this presentation we're going to talk about polynomial congruences and also over here about the Pollard row method for factorization. The two are not directly related, they were just in somewhat consecutive sections in the book, and the Pollard row method is so quick that I didn't make a separate set of slides, sorry about that. So for the most part we'll be talking about polynomial congruences. Let's take a look at what they are. Basically, if we think back at our careers in algebra, if you will, then at some point in time we've learned to solve linear equations. And after we have learned to solve linear equations, there are two possible natural next steps. Namely, we could turn our attention to higher order equations, such as quadratic equations. And of course, that is something that we have done in our mathematical careers. And in the context of congruences, those would be polynomial congruences, the subject of this talk. And we could also talk about systems of linear equations, which in the context of congruences would be systems of linear congruences. Now, we will consider polynomial congruences. And as far as I can see at this stage, we won't need systems of linear congruences in this course except for the Chinese remainder theorem, which we've already discussed. And overall, also what I can see from my admittedly not very expert perspective is that systems of linear congruences are similar to systems of linear equations, which means really that if your linear algebra is good, it should be a reasonably quick read. And if you had not had linear algebra, it may be better to first take that course. So let's take a look at polynomial congruences. A key lemma that basically breaks up the task of solving a polynomial congruence or polynomial equations, modular equations in general, is that if you've got a prime factorization of your modulus to be the product from j equals 1 to k pj to the aj, with pairwise distinct primes pj, then x solves the equation f of x equals 0 modulo m if and only if for all j, x solves the equation f of x equals 0 modulo pj to the aj. So that means that when you've got a really big modulus in terms of the modulus having a lot of factors, then what you can do is you can break that down into a smaller modulus by taking care of the prime power factors of the modulus first. So what's the proof? Well, the direction left to right is trivial, because if m divides f of x, which is what it means that f of x is equivalent to 0 modulo m, well, then all of its factors do also, and that means that f of x is equivalent to 0 modulo pj to the aj. For the other direction, well, we note that if for all j, x solves the equation f of x equals equivalent to 0 modulo pj to the aj, then for all j, pj to the aj is a factor of f of x. But that means, because the pj are pairwise distinct, the product of the pj to the aj is contained in the prime factorization of f of x. And that means that m divides f of x, that is, that f of x is equivalent to 0 modulo m. And that is the proof already. So that means that if we want to solve any kind of equation, and we're going to talk about polynomial equations here, but if we want to solve an equation f of x equivalent to 0 modulo m, really what we need to do is we need to first solve the same equation modulo pj to the aj, and well, that means so to solve that we first solve the congruences modulo pj to the aj, and then we use the Chinese remainder theorem to piece together the result for the rest. Okay, so how do we solve the congruence f of x equivalent to 0 modulo pj to the aj? Well, let's first take a look at a simple congruence modulo 7. And well, x squared plus 2x plus 46 equivalent to 0 modulo 7. Well, 46 modulo 7 is 4, right? So that's x squared plus 2x plus 4 equivalent to 0 modulo 7. And now we just check. Well, if we plug in 0, we don't get a multiple of 7. If we plug in 1, we get 1 plus 2 plus 4, which is 7, which is, of course, equivalent to 0 modulo 7. Plug in 2, we get 4 plus 4 plus 4, that's 12, that doesn't work. Plug in 3, we get 9 plus 6 is 15, plus 4 is 19, that doesn't work. Plug in 4, we get 16, plus 8 is 24, plus 4 is 28, that does work. Plug in 5, we get 25 plus 10 plus 4, that's 34, and it does not work. And if we plug in 6, we get 36 plus 12 is 48 plus 4 is 52, and that does not work. And so the solutions are x equals 1 and x equals 4. Great. So thankfully, at least for modular that are powers of primes, which is what the rest of this presentation on the polynomial congruences will be about, at least for those we have a more systematic approach. However, we first need to have the solutions modulo the prime number. And again, I only play a number theorist on TV. If there are better ways to find these solutions of polynomial congruences modulo prime numbers, I am not aware of them, unfortunately. So we're going to assume in the following that we have the solutions modulo the prime number and then see how we can find solutions modulo the prime powers. Okay, so we need a definition, and that is if we've got a polynomial, which is sum j equals 0 to n aj x to the j, then the derivative of this polynomial is f prime of x being the sum j equals 1 aj j times x to the j minus 1, which is something that you ought to be familiar with from calculus, because of course what happens when you take the derivative, the constant term goes away, so you get a 1 where it starts, and you differentiate these terms with the power rule. Nothing special here. However, we have not built number theory on calculus, so technically this is just an abstract definition. And in abstract algebra, actually, when you talk about formal power series and the like, then very often it is really set up that way. And for formal power series, that makes sense, because when you do algebra, you don't want to be bothered with the radius of convergence and things like that. Thankfully, however, the derivative behaves just like we would expect it from calculus, and so we will use the usual rules without hesitation. Even though the bigger one, and the next one is one of those, we will also prove. So, theorem. If you've got a polynomial of degree n, and a and b are real numbers, then f of a plus b is equal to the sum k equals 0 to n, kth derivative of f at a divided by k factorial times b to the k. So this is something that comes straight through calculus. And all the terms f to k of a k divided by k factorial are polynomials in A with integer coefficients. Okay, that is basically nothing else but Taylor's theorem applied to polynomials, where we choose the degree of the Taylor polynomial so that the Taylor polynomial is equal to the original polynomial. So that does make a good bit of sense. However, in case we don't have Taylor's theorem available right away in memory, and also because we're building things up algebraically, let's prove the whole thing with the binomial theorem. So you take f of a plus b, which is the sum j equals 0 to n cj a plus b to the j, and you can use the binomial theorem on that term, so you get the sum j equals 0 to n cj times sum k equals 0 to j, because that's what the exponent was here, j choose k, a to the j minus k, b to the k. Just the binomial theorem. Now we're going to switch the order of the summations, and when you look at this summation, you realize that k is always less than or equal to j in here in this double sum, and we can also express that as the sum k less than or equal j, or j greater or equal than k. And when we know that j is greater or equal than k, then we know that k runs from 0 to n, and j runs from k to n. That way j is always greater or equal than k. Other than that, we keep the cj, we keep the j choose k, we just chose to write it out here, and we've got a to the j minus k and b to the k also copied down from the above. Now this sum is a sum over j, which means stuff that only depends on k, or stuff that doesn't depend on j, can be pulled out. So this is the sum k equals 0 to n b to the k, 1 over k factorial, this is the k factorial, this is the b to the k, times the rest, sum j equals k to the n, here's the cj, here's the j factorial over j minus k factorial, and here's the a to the j minus k. But here you realize that this is just the kth derivative of a to the j, it should be. That should be the kth derivative of a to the j. And so that means this is the kth derivative of the polynomial, because when you take the kth derivative of a polynomial, the 0 through k minus first terms all go away. And so that means this to sum k equals 0 to n b to the k, 1 over k factorial fk of a, and we also automatically have shown that fk of a is really a polynomial in a, with, what did we say, integer coefficients if the polynomial has integer coefficients. I don't think we said anything about integer coefficients, but I'm not going to scroll back right now. We move on. So the important theorem is actually called Hensel's lemma, because it is an auxiliary to solving polynomial congruences, and so that explains the lemma in Hensel's, is because Hensel is the one who proved it, presumably. Take a polynomial with integer coefficients and a prime number, and we let k greater or equal than 2 be an integer. And we let R be a solution of the congruence f of x equivalent to 0 modulo p to the k minus 1. Well then, if the derivative of the polynomial at R, at the solution R, is not equivalent to 0 modulo p, then there is a unique integer t between 0 and p minus 1, so that f of R plus t times p to the k minus 1 is equivalent to 0 modulo p to the k. So we take a solution modulo p to the k minus 1, and from that we construct a solution modulo p to the k, which means once we've got solutions modulo p, we can build things up, at least as long as that derivative is not equivalent to 0. Well, first of all, let's finish this out. If this is a unique solution, it would be nice to have a formula for it, and that solution, or that number t, is given by t equivalent to negative f prime of r bar f of r divided by p to the k minus 1 modulo p, where f prime of r bar is a multiplicative inverse of f prime of r modulo p, and this notation actually is also fairly common throughout algebra and number theory, that a bar is used for a multiplicative inverse in this arithmetic. An exponent negative 1 would probably be more common here, but I think that would just raise confusion because we already are using exponents here in other capacities. Well, that of course leaves the question, what happens when the derivative is not 0, and when the derivative is not 0 at r, or not equivalent to 0 modulo p at r, and if f of r is equivalent to 0 modulo p to the k, well then we have that f of r plus t times p to the k minus 1 is equivalent to 0 modulo p to the k for all integers k. So, well, that basically means if we already have a solution modulo p to the k, which is what we're looking for, and of course once you've got a guess like this r, you can test that, well then you don't just have one solution, but you've got a bunch of solutions. And finally, if this derivative is equivalent to 0 modulo p, and f of r is not equivalent to 0 modulo p to the k, then f of x is equivalent to 0 modulo p to the k. That congruence modulo p to the k has no solutions that are equivalent to r modulo p to the k minus 1. So it's not that it doesn't have any solutions at all, it just doesn't have any solutions that can be reduced back to the solution that comes from the congruence modulo the smaller power of p. Okay, so how do we prove that? Well, the idea of the proof is that if you've got a number s, which is r plus t times p to the k minus 1, and if you suppose that that solves the congruence f of x equivalent to 0 modulo p to the k, well then s solves the congruence f of x equivalent to 0 modulo p to the k minus 1. Sure, that is because if something is divisible by p to the k, then it's definitely divisible by p to the k minus 1. And then we have the following. We've got 0 equals f of s, which is f of r plus t times p to the k minus 1, which is, of course, now by this Taylor-like theorem that we had, that's f of r plus this Taylor expansion, where we expand about r, and our disturbance is the t times p to the k minus 1, right? And that is equivalent to f of r plus f prime of r t times p to the k minus 1, as long as we're going modulo p to the k. And that is because as soon as we've got p to the k minus 1 quantity squared, of course, as long as this is not, as long as k minus 1 is not equal to 0, which we would certainly exclude, we will have that all these terms in the back here are divisible by p to the k, and therefore they go away. Okay, but what that means is that f prime of r t p to the k minus 1 will be equivalent to negative f of r modulo p to the k. And that means that we can solve for the t under various conditions, right? However, we can also do a few things here first, namely, f of r was equivalent to, or we are going to ultimately assume that f of r is equivalent to 0 modulo p to the k minus 1, which means f of r is divisible by p to the k minus 1. That's what we assume all along, which means we can take this equation and divide by p, this congruence, and divide by p to the k minus 1, and get something that also works, but this time it works modulo p, because of course we also have to divide it out of the modulus. Okay, for all t that satisfies this congruence above, we have that s equals r plus t times p to the k minus 1 will solve the congruence modulo the power p to the k, and that basically would be that we just trace the argument backwards, go bottom up, but all the steps are allowed, and vice versa, and that's how we gave the argument. If we have a solution, then it must, or if we have a t so that all this stuff works out, then t must satisfy this thing here. Okay, and so now we're going to prove parts 1, 2, and 3 of Hensel's lemma. And the key to all three parts, even though part 1 just says that f prime of r is not equivalent to 0 modulo p, is that we have to solve the congruence f prime of r times t equivalent to negative f of r over p to the k minus 1 modulo p. And, well, what can we recall? The greatest common divisor of f prime of r and p is, if we call that thing d, then this linear congruences has exactly d incongruent solutions modulo p. And it has those when d divides the right-hand side, and it doesn't have any otherwise. And that's a theorem that we've proved earlier on about congruences of the form ax equivalent to b modulo p. Okay, so because f prime of r is not equivalent to 0 modulo p, that means that the greatest common divisor of f prime of r and p is 1. And that means the linear congruence has exactly one solution. And this solution is, of course, then obtained by just multiplying the dividing, technically, or essentially dividing by the f prime of r, and that means we multiply with the multiplicative inverse of the f prime of r, and we get t equivalent negative f prime of r bar times f prime of r divided by p to the k minus 1 modulo p. And yeah, that's where f prime of r bar is a multiplicative inverse of f prime of r modulo p. Okay, well, we're going to continue now to part 2. And part 2 is that f prime of r is now equivalent to 0 modulo p, but we also have that f of r is equivalent to 0 modulo p to the k. We still have the same thing. We have this congruence that we have to deal with, and we know that it has exactly d incongruent solutions, with d being the greatest common divisor of f prime of r and p. Well, f prime of r is equivalent to 0 modulo p, and that means the greatest common divisor of f prime of r and p is p. And yeah, that's one of our assumptions here, right? And because f of r is equivalent to 0 modulo p to the k, that's the other one, we have that p also divides f of r divided by p to the k minus 1, and that means all integers solve this linear congruence because both sides are already divisible by p, and I can stick in whatever I want in the t and things will still work out. So we conclude that f of r plus t times p minus p to the k minus 1 is equivalent to 0 modulo p to the k for all integers t. We come to, and again we're going to keep this part here, only the top headline will change. We go to part 3, which is that f prime of r is equivalent to 0 modulo p, and now f of r is not equivalent to 0 modulo p to the k. We have the same thing. We've got to think about solving linear congruences. f prime of r is equivalent to 0 modulo p. Therefore, we have that f prime of r has greatest common divisor p with p. But f of r is not equivalent to 0 modulo p to the k, right? Which means that p does not divide f of r divided by p to the k minus 1. And that means that the greatest common divisor, that this is not true, and that means we're in the otherwise case, and so that means we have the none otherwise. So hence no value of t provides a solution in this case. And that's the end of the proof of Hensel's lemma. Corollary to the whole thing is that if you've got a solution of the polynomial congruence f of x equivalent to 0 modulo p, where p is prime, and if f prime of r is not equivalent to 0 modulo p, and here's something that is of course very nice, that for the f prime of r equivalent to 0, we always stay with modulo p. So we don't have to worry about multiplicative inverses modulo p squared, p cubed, and so on and so on. But if that's the case, then for every k there is a unique solution rk of f of x equals 0 modulo p to the k that was obtained from r, and that is that we've got r1 equals r, and rk is rk minus 1 minus f rk minus 1 f prime of r bar, where the f prime of r bar is a multiplicative inverse of f prime of r modulo p, and that comes directly from Hensel's lemma, because when f of rk minus 1 is equivalent to 0 modulo p to the k minus 1, and f prime of r is not equal to 0 modulo p, then we have that rk, then we have that rk being equal to rk minus 1 plus negative f prime of r bar f of rk minus 1 divided by pk minus 1, p to the k minus 1 times p to the k minus 1. That, which is exactly, of course, what is claimed up here, is the next solution. So that satisfies f of rk equivalent to 0 modulo p to the k, and we have proved the corollary. Okay, so let's solve one, actually. We want to find the solutions of the congruence x squared plus 2x plus 46 equivalent to 0 modulo 2401. Well, note that 2401 is 7 to the 4th. Yeah, and that's, I know that, of course, because I've set it up and we can verify it, because 7 times 7 is 49. If you multiply that by 7, you end up with 343. And if you multiply 343 by 7, you end up with 2,100 plus 280 plus 21. So that's 2,100 plus 301, which is 2,401. Now recall from the prior example that x equals 1 and x equals 4 solve x squared plus 2x plus 46 equivalent to 0 modulo 7. Recall from calculus that f prime of x is 2x plus 2, and that means f prime of 1 is 4. Here, just plug it in. F prime of 4 ends up being 10, which is equivalent to 3 modulo 7. And that means the multiplicative inverse of f prime of 1 is 2, because 2 times 4 is 7, which is 1 modulo 7. The multiplicative inverse of 4 is 5 modulo 7. Whoops. The multiplicative inverse of f prime of 4, which is 3, is 5, because 3 times 5 is 15, which is 1 modulo 7. Yeah, okay. We'll work out the solution set, or the solution that comes from x equals 1. The other computation is, of course, a good exercise, but it isn't any different in principle. So our first solution for modulo 7 to the first, is 1. The next solution, R2, is R1 minus f of R1 times f prime of 1 bar, which is 1 minus, and now f of R1 I claim is 49. So let's see. Yeah, sure. Plug in 1, I get 1 plus 2 plus 46 is 49, and I have the 2, which is this multiplicative inverse here. And, well, that means that this is negative 97, right? And if you work that out, negative 97 is 1 modulo 7 squared, and that's because the difference between those two is 98, and 98 is 2 times 49, which is 2 times 7 squared. So that works out. That is rather lucky. I didn't set this example up expecting that, but it just happened to work out that way, and I'm very happy about that, because that means computing R3 is rather quick, because we use R2 minus f of R2 minus f prime of 1 bar, and so that gives us again 1 minus 49 times 2, but this time around we're going modulo 7 cubed, which is 343, so this time it stays with negative 97, and that's it, because this time we don't wrap around, or this time we wrap around a larger modulus, and so that means this time around for R4, whereas negative 97 is the solution of this congruence, is a solution of this congruence modulo 343, to now find a solution modulo 7 to the fourth, we need R4 equals R3 minus f of R3 f prime of 1 bar. Of course, the nice thing is f prime of 1 bar is still 2. The other nice thing is that R3 is negative 97. We can just copy that down. And the not so nice thing is that f of R3 is 9,261, and that's of course something that we work out with a calculator, and we're also going to work out, yeah, I'm not going to do the mental acrobatics here, I'm getting a little tired. If you work that out, that's negative 18,619, and that is equivalent to 589 modulo 7 to the fourth. I mean, that is all stuff where you just use a machine, or at least I did use a machine. Yeah, I mean, the arithmetic is within range, but I really don't want to do that in my head right now. Double check, however, that's then very important. If I just take 589 squared plus 2 times 589 plus 46, I end up with, and again, calculators, 348,145, and that is 145 times 7 to the fourth, again, calculator or MathCat telling it to factor, and that is equivalent to 0 modulo 7 to the fourth, and that takes care of this example. And so in this fashion, polynomial congruences can be solved as long as we have a solution of the congruence modulo the prime number that underlies or that starts this whole sequence. Okay, so Pollard's row method now is a completely different story, so if you want to, you could just take a break right now and come back to Pollard's row method later. You know how this sometimes goes in a longer class. You have 20 minutes left, that's good enough to cover another section, so you don't want to waste time, but at the same time, you've got to mentally reset, so feel free to hit pause here, come back to it later if you wish. So we want to look at a randomized approach to factoring, and when you're looking at randomized algorithms, they are not guaranteed to succeed. So a randomized algorithm just tries a couple of things, and if it doesn't find the factorization, you really don't know whether there is one or not. However, if there is a result, certain randomized methods are very likely to find it quickly. That is something that is very surprising about randomized methods. And so one of them is Pollard's row method, where we take a large composite integer and let p be its smallest prime factor. If now x0 through xs are pairwise distinct modulo n, but for some I not equal j, we have that xi is equivalent to xj modulo p, modulo this prime factor, well then p divides the difference of xi and xj, and n does not divide the difference of xi and xj because both numbers are smaller than p and therefore smaller than n, and that means the greatest common divisor of n and xi minus xj will be a non-trivial factor of n. And we need to insist here that n does not divide xi minus xj, because otherwise the greatest common divisor of n and a number could be n, which would be rather trivial. Okay, so note that in order to therefore find a factor with the very efficient Euclidean algorithm that finds greatest common divisors, we only need the elements xi and xj. Well, probabilistic arguments, however, show that you've got a really good chance to find these elements xi and xj by randomly choosing numbers x0 through xs, so that s is large compared to root p and small compared to root n. These arguments are beyond the scope of this course. They are quite deep, I would suppose, but we're not going to further prove them here. And so apparently this approach is practical, because a typical approach to attempting a factorization of a number n is to do the following. You first try to divide n by any prime number smaller than 10,000. because that's just, you just rule out the trivial prime factors. And then you try to use the Pollard row method, which is founded on what we've just seen in the previous, to find a prime factor of size up to 10 to the 15. Well, if the Pollard row method is effective for prime factors up to, for working between root p and root n, that means that root 10 to the 15 is 10 to the 7.5, and 10 to the 10 can be considered large compared to that number, so you would use Pollard row with 10 to the 10 elements, and it's small compared to a number 10 to the 12, so we don't have to worry. So this will work for numbers that get beyond 10 to the 24th, because this thing has to be smaller than, significantly smaller than root of n. Okay, so the probabilistic note from the previous panel says that there's a good chance to find any existing prime factors up to size 10 to the 15 in 10 to the 10, which is 10 billion steps with the Pollard row method. And if each step takes a microsecond, and note that a microsecond is about 2,000 processor cycles, so that is, I would think, a conservative estimate. Estimation on a PC would take about 1,000 seconds. And yeah, that is not that long at all, because 3,600 seconds is an hour, so this takes less than a third of an hour, so it takes less than 20 minutes. Okay, so now let's try to reduce the number of operations a little bit to just generate all these numbers. And so for a polynomial f, we would create a recursive sequence, xk plus 1 being f of xk. And eventually there will be an I and a j, so that xi is equivalent to xj modulo n. And from there on, of course, xi plus z will be the z power of the polynomial applied to xi. So this is the polynomial applied to xi consecutively, z times. So it's f of xi, f of xi, f of xi, and so on. Tied my tongue up there a little bit, so this is not an algebraic power. This is repeated application of the polynomial. That will be equivalent to fz of xj, because after all, when we have inputs that are equivalent modulo n and we stick those into a polynomial, then the outputs will also be equivalent modulo n. So at some point in time there, the xi plus z and the xj plus z will just be the same things now. And so if you picture this sequence with the loop at the end, basically the image looks like a row, right? Because you start with small numbers, the numbers get larger, and then it starts looping around. And that is really where the name of the Pollard row method comes from. So it's really more of an idiosyncratic thing. Somebody visualized it that way and thought it looked like a row, and probably it was Pollard himself, or I would think it could have been Pollard himself, and that's where the name comes from. Okay, so if s is the smallest multiple of the first difference j minus I where this happens, that is at least as large as the j, then actually xs will be equivalent to x2s modulo n, and so the search actually finds greatest common divisors of x2k minus xk and n, and that is now not a conclusion, that is just how the search is being set up, because then once you realize that this thing is 0, you realize you have to terminate the search or do something else. So then, practically speaking, if a non-trivial common divisor is found, you stop, and that, well, you stop and you have found a non-trivial factor of n, sure. And if a divisor turns out to be n, you also stop, and then it is time to try something else in the Pollard row method. And so in practice, f of x equals x squared plus 1 is a good function to generate the x sub j. And the seed x0 equals 2 is also a good start. These are things that people have tried out who really are rather deep in the matter. And, well, then we just run the Pollard row method. And so, for example, here I have a number, 8675321. So it's close to my favorite prime number, 8675309. I'm saying f of x equals x squared plus 1. I'm using x0 to be 2. That's seed for the Pollard row method. And I'm going to execute just 2,000 steps just to show things here. And of course, if I now just work out in brute force xk being f of xk minus 1, then very quickly the numbers get large, and note that the last one is already affected by rounding errors because this number will not end in a bunch of zeros. But we're interested in moduli, modulus n, and so what we're actually going to do is we're going to set up xk to be f of xk minus 1 modulo n, and that's what this operation does here. So we need to be careful with rounding here too, because even in modular arithmetic, MathCAD first computes the square and then it computes the modulus. So this sheet, if I'm looking at it more generally, for 7-digit numbers it'll still work out, but as soon as we get 8-digit numbers, the square would have 16 digits and the internal arithmetic is limited to 15 digits. So what we get is that these numbers x now look like this, modulo n, and I have generated 2t such numbers, and now I'm going to look at the difference of x2j minus xj. I'm going to take the absolute value here. I'm not sure if I even need to do that for this function, but can't hurt to have positive numbers. And I'm computing the greatest common divisor of any of these numbers with n. And what I get is I get greatest common divisors being 1. Hey, that is not a problem. I mean, that happens, right? But after 6 steps, I find that one of the divisors of this number is 17. And that is, of course, very nice. Because if I just use the factorization algorithm in MathCAD, I realize that this thing is factored into 17 times 29 times 17,597. So, okay, trial divisions on a larger machine would have certainly yielded that thing very quickly. I mean, maybe even trial division by hand. So let's take a look. I made a little note to myself here on the slides, and that is 50,107 worked well. So did these other two numbers. So let's take a look at 50,107 real quick. That's of course a smaller number than this one, 50107. Well, you see, you can see here in the factorization that is a number that has nastier prime factors, right? And the Pollard Rowe method, still in 5 steps, produces actually the uglier of the 2 prime factors. And you can see that, again, of course, that's not a guarantee, but the way it works nicely here for comparatively small numbers should be an indication that after trial divisions have been exhausted for prime numbers up to 10,000, that then the Pollard Rowe method hopefully will find decent prime factors for anything between 10,000 and 10 to the 15th. With that, I'll leave you to the homework for 2 drastically different sections, and I'll see you in the next presentation. Bye.